in 1848, there was this spark that ignited during a routine explosive packing job on a railroad.
Oh, wow.
Yeah, and this massive, like 3-foot iron tamping rod rocketed upward. It entered right under a 25-year-old man's cheekbone, passed behind his left eye, and shot completely out the top of his skull.
And incredibly, he lived.
He lived to tell the tale, which is just, it's wild. Anyway, welcome to another custom-tailored deep dive. Today, we are exploring the incredibly complex biological machinery that actually makes you, well, we're talking about the human brain and the spinal cord.
Right, arguably the most intricate structure in the known universe.
Exactly. And because we are dealing with something so complex, we're going to embrace a specific dynamic today. I will be stepping into the role of the eager student, asking all the questions, while my co-host here takes on the role of the lecturer to guide our lesson.
I am definitely ready for the challenge. I mean, it's a massive topic, but we have a really brilliant roadmap for this lesson. We are drawing our insights straight from section 3.4 of chapter 3 from Psychology 2E.
And it really is a treasure trove of information.
Yeah.
By the end of this deep dive, you, the listener, are going to understand how that man with the iron rod through his skull completely changed science.
Yeah.
Why your fingers command way more brain power than your legs, and like how we even know any of this in the first place.
Right, but to understand the brain, the textbook actually starts slightly lower. We have to look at the spinal cord first.
Yeah, and I've always thought of the spinal cord as just a biological extension cord. I mean, is it essentially just dumb wiring connecting the supercomputer in the skull to the rest of the body?
It's a really tempting way to visualize it. I mean, I get that. But it definitely undersells what the spinal cord actually does. It's a highly intelligent relay station.
Yeah.
Structurally, it merges seamlessly with the brainstem and travels down your back, stopping just below the ribs. And it's divided into 30 functional segments that correspond to your vertebrae.
Right, with all the nerves branching out.
Exactly. You have sensory nerves bringing information in and motor nerves sending commands out. But here is the thing. It doesn't always wait for the brain's input to act.
Okay, let's unpack this. Are you saying the spinal cord makes decisions on its own?
Under very specific circumstances, yes. We call these reflexes. Think about touching a blistering hot stove or getting that knee-jerk reaction when a doctor taps your tendon.
Oh yeah, you just immediately pull back.
Right. When a sensory message hits certain extreme parameters, like intense heat, the signal travels to the spinal cord and goes right into a local processing center there. That center instantly fires back a motor command to pull your hand away.
So it completely bypasses the brain.
It does. I mean, it eventually informs the brain so you feel the pain and realize what happened, but the action of pulling away happens first.
That's wow.
Yeah, in a survival situation, waiting for a signal to travel all the way up to your cortex, get processed, and travel all the way back down could result in severe tissue damage. So the spinal cord saves you crucial fractions of a second.
That structural independence is amazing, but it kind of makes me wonder about vulnerabilities. If it's organized segment by segment, what happens when that relay station gets physically severed or damaged?
Because of that top-down organization, an injury at any specific segment cuts off all the segments below it from the brain.
Oh, man.
Yeah, so the brain can no longer send motor commands down, and sensory information can no longer travel up. That results in paralysis. The lower on the spine an injury occurs, the fewer bodily functions are lost, simply because fewer segments are cut off.
Which is a devastating reality.
Yeah.
But Section 3.4 doesn't linger purely on permanent damage, right? We pivot into something incredibly hopeful, which is the nervous system's ability to heal and adapt.
Yes, exactly. This is the concept of neuroplasticity. We used to think the adult brain was this fixed, static machine, but it's actually highly malleable. It can change, adapt, and literally rewire itself in response to experience or trauma.
Right. The text highlights Bob Woodruff for this, right? The ABC reporter.
Yeah, he suffered a severe traumatic brain injury from an improvised explosive device in Iraq. He faced massive cognitive deficits, struggling to remember things or find the right words. Yet, through intense therapy over time, he made a remarkable recovery.
And that recovery isn't just him learning, workarounds, right?
Yeah.
His brain physically changed. The textbook mentions it creating new synapses, pruning old unused ones, and changing glial cells.
Yeah, glial cells.
Which, if I'm understanding right, are basically the support staff for your neurons, providing them with nutrients and insulation.
That's a great way to put it. The text even mentions neurogenesis, which is the actual birth of brand new neurons.
That's incredible.
That's the essence of neuroplasticity. Your experiences are constantly sculpting the physical architecture of your brain. And to really grasp how that rewiring works, we should look at the macro structure of that architecture.
Yeah, let's do that. Visualizing the surface of the brain, the cerebral cortex, it's famous for those wrinkles. It's covered in bumps called gyri and grooves called sulci. And there is one groove that dominates the entire landscape.
Well, longitudinal fissure. It's
Yeah.
this deep canyon running straight down the middle, separating the brain into the left hemisphere and the right hemisphere.
Okay.
And there is a specialization of function between the two, which we know as lateralization. Decades of research show the left hemisphere is often superior for forming memory associations and selective attention, while the right hemisphere handles things like pitch perception and arousal.
But the textbook is very careful to warn against that pop psychology myth, right? The whole left-brained logical people versus right-brained creative people thing. The two halves are constantly collaborating.
Oh, absolutely. They have to, and they do so via the corpus callosum.
The corpus callosum.
Yeah, this is a massive anatomical bridge made of about 200 million neural fibers, or axons, connecting the two hemispheres. It's basically a high-speed data cable ensuring that whatever the right side is processing, the left side knows about instantly.
Now, what's fascinating here is, what happens when doctors intentionally cut that high-speed cable? The textbook brings up cases of severe epilepsy, where the electrical storm of a seizure spreads across the whole brain.
Right.
And to stop it, surgeons will literally sever the corpus callosum.
It creates what we call split brain patients, and it gives researchers an unprecedented window into what each isolated hemisphere does. Now, to understand this, you need to know about contralateral control.
Right. Opposites.
Exactly.
Yeah.
In general, the left hemisphere controls the right side of the body, and the right hemisphere controls the left side of the body.
Here's where it gets really interesting. Let's say a split brain patient is sitting in front of a screen. You flash a picture of a key to their left visual field.
Okay.
Because of how our eyes wire into the brain, that visual information is sent exclusively to the right hemisphere. But the speech center, for most people, is located in the left hemisphere.
Right, so the right side of the brain sees the key, but it doesn't have the words to say key.
Exactly. If you ask the patient, "What did you see?" the verbal left hemisphere answers. And since it genuinely didn't receive the visual data, the patient will verbally reply, "I didn't see anything."
Because to that half of the brain, nothing happened.
Yes, but, and this is the part that just blows my mind, if you put a pen in their left hand, which is controlled by the right hemisphere that did see the image, they can draw a perfect picture of the key.
Wow.
Right. And the moment they finish drawing it and they look at the drawing with both eyes, the verbal left hemisphere finally receives the information and can suddenly say, "Oh, it's a key."
The brain is physically severed, so it resorts to passing notes to itself in the outside world. It's incredible.
It perfectly illustrates how localized certain functions are.
Yeah.
Now, if we stay on the surface, the forebrain, which is the largest part of the brain, is divided into 4 distinct lobes. So, as the lecturer today, take us through the front of the brain first.
Sure. Well, the frontal lobe is essentially your executive control center. It sits right behind your forehead. It's responsible for reasoning, motor control, emotion, and language.
Got it.
A prime example of its localized function is Broca's area, which handles language production. The textbook details the case of Padma, an electrical engineer who suffered damage specifically to this area.
Yeah, Padma's situation really highlights the difference between understanding language and producing it. She can read, she can follow directions, she can go about her day, her vocal cords work perfectly fine.
Right.
But she cannot form the words to speak or write. The thoughts are just trapped inside her head without the mechanical output to share them.
It's tragic. Now, a completely different aspect of the frontal lobe is the prefrontal cortex, which governs judgment and impulse control. Look at another case study from the text Fiona.
Oh, right, the grocery store story.
Exactly. She's a woman who suffered a stroke in her right frontal lobe. Aside from some paralysis on her left side, due to that contralateral control we discussed, her personality dramatically shifted. She lost her social inhibition.
Right.
She would be in the grocery store and just start eating fruit from the bins without paying, something she never would have done before the stroke.
And that loss of impulse control brings us right back to the hook of today's deep dive, Phineas Gage and the iron rod. When that rod blasted through his skull in 1848, it ripped right through his frontal lobe.
Right.
But more importantly, it severed the neural pathways connecting his frontal lobe to his limbic system, which is where raw emotions are processed.
So the executive planning center lost its connection to the emotional engine. And according to the stories from his friends, he was no longer Gage. He transformed from a well-mannered, reliable foreman into an impulsive, unpredictable man.
But, and this is important, Section 3.4 brings up a really crucial caveat about the Gage story, and I want to highlight this. The textbook points out that those dramatic personality changes were likely heavily exaggerated.
Yes.
Why? Because 19th century scientists were in the middle of a massive heated debate about whether brain functions were localized or distributed. Since the actual medical documentation on Gage's life after the accident was very sparse, scientists on both sides of the debate just manipulated his story to fit their pre-existing arguments.
Which is wild to think about.
It is. It's a stark reminder that even hard science is sometimes filtered through human bias.
It is an excellent point. So moving just behind the frontal lobe, we find the parietal lobe. This area specializes in processing information from the body's senses. The star of the parietal lobe is the somatosensory cortex.
And that's a strip of tissue that registers touch, temperature, and pain from all over your body, right?
Exactly.
And the way the body is mapped onto this cortex is wild. If you laid out a map of your body on the brain surface, it wouldn't look like a normal human. It's entirely distorted. The amount of brain tissue dedicated to a body part is not based on the physical size of that part, but on how sensitive it is, like how many nerve endings it has.
Yes, your back and your thighs take up very little real estate on this map, but your lips, your tongue, and especially your fingers command massive amounts of brain processing space.
Right.
It reflects how we actually navigate the world, you know?
Wow.
We feel our way through our environment with our hands and faces.
And that map can change, right? The text connects this back to neuroplasticity by mentioning phantom limbs in amputees. When a limb is lost, the somatosensory cortex doesn't just leave that brain tissue empty, it reorganizes itself. Other body parts will literally take over that real estate.
It's remarkably efficient.
Okay, so that handles movement, executive function, and touch. What about hearing and vision?
On the sides of your head, near your temples, you have the temporal lobes. These handle hearing, memory, and emotion. They house the auditory cortex and Wernicke's area. Wernicke's area is crucial for language comprehension.
Oh, so this is the exact opposite of Padma's problem with Broca's area. If you have damage to Wernicke's area, you can easily produce fluent, flowing speech. But it often doesn't make any sense, and more importantly, you can't understand language that is spoken to you.
Right. Finally, at the very back of the skull, we have the occipital lobe. This is the visual processing center. The textbook points out that it is organized retinotopically.
Meaning there is a direct point-to-point relationship between what hits your retina and where it's processed on the cortex. It's almost like a distorted movie screen at the back of your head, mapping out your visual field.
That's a great analogy. So that covers the outer shell, the cerebral cortex. But there is an entire world of structures buried deep beneath that surface in the forebrain.
The subcortical structures.
Mm-hmm.
This is where we find the thalamus. I like to think of it as the brain's grand central station for the senses. Every sense you have routes through the thalamus before being sent off to its dedicated processing lobe, except for one.
Right, smell is the great exception. The olfactory system bypasses the thalamus entirely and projects directly into the limbic system.
Which explains so much. The limbic system is a network of structures heavily involved in processing emotion and memory.
Exactly.
Because smell has a direct VIP ticket right into the emotional center, a certain perfume or the smell of rain on asphalt can trigger a visceral emotional memory in a way that just seeing a picture simply can't.
It's a very powerful connection. Let's break down that limbic system. It includes the amygdala, which is vital for tying emotional meaning to our memories.
Okay.
It contains the hypothalamus, which acts as the body's thermostat, regulating homeostasis, temperature, appetite, blood pressure. And then there is the hippocampus, the structure absolutely essential for forming new explicit memories.
If we connect this to the bigger picture, the function of the hippocampus was largely discovered through one of the most tragic and famous cases in medical history.
Right, Siege.
Yes, Henry Gustav Molaison, known for decades only as HM. In 1953, he was suffering from severe, debilitating seizures. In a desperate attempt to cure him, surgeons removed his hippocampus and his amygdala.
The surgery did reduce his seizures, but it completely destroyed his ability to form new explicit memories.
Right, he could remember his childhood, but from the moment he woke up from surgery, his life was basically frozen in time.
Yes. If you introduced yourself to him, had a pleasant conversation, and left the room for a few minutes, he would have no idea who you were when you walked back in. He couldn't remember what he had for lunch. He couldn't remember that his uncle had passed away and would experience fresh grief every time he was told.
It's heartbreaking. But the breakthrough The reason HM changed neuroscience was that while his explicit memory was gone, his implicit memory was still intact.
Right.
Researchers found they could teach him new physical skills. For example, they could teach him to trace a star while looking in a mirror. He would sit down, do it terribly on day 1, and by day 3, he was an expert. Yet he had zero conscious memory of ever practicing the task.
Which forces us to ask, how is a brain learning without a hippocampus? It tells us that procedural memory, the memory of how to physically do something, must live somewhere else.
Right.
And that takes us deeper into the brain, beneath the forebrain, into the midbrain and the hindbrain.
So the midbrain connects the forebrain and the hindbrain. It contains the reticular formation, which runs like a rod up the center and regulates our sleep-wake cycles and arousal.
Yes, and it also houses the substantia nigra and the ventral tegmental area. Those two areas are critical for producing dopamine. They manage movement, mood, and reward.
And when neurons in those areas degenerate, that's what leads to Parkinson's disease.
Exactly. Below the midbrain is the hindbrain, which looks like a flared-out extension of the spinal cord. It houses the cerebellum, which coordinates balance and fine motor movement.
So the cerebellum is exactly where procedural memories like HM, tracing that star, are processed.
Spot on. And right next to the cerebellum, we find the medulla and the pons. The medulla handles the absolute basic automatic processes of life, breathing, blood pressure, heart rate. The pons acts as a bridge connecting the brain and spinal cord, and also helps regulate sleep.
And together with the midbrain, this is known as the brainstem, right?
Correct. And this functional division, the cortex handling conscious thought, while the brainstem quietly keeps the lungs breathing and the heart beating, creates some of the most profound medical and ethical dilemmas we face as a society.
So what does this all mean? When the higher brain dies, but the lower brain keeps the body functioning, how do we define what life is?
This raises an important question, and it is a reality the textbook illustrates through the 1990 case of Terra Schiavo. Now, before we get into this, to be absolutely clear to you listening, we are impartially reporting the medical and legal facts exactly as they are laid out in the textbook.
Right, exactly. We're not taking a side on the deeply personal, ethical, or political debates surrounding end-of-life care. Our goal is simply to examine the physiological reality of brain death.
Yes. So according to the textbook, Terra Schiavo suffered a massive cardiac arrest triggered by a bulimic episode. Her brain was deprived of oxygen. While she was resuscitated, the lack of oxygen completely destroyed her cerebral cortex.
Wow.
Scans confirmed there was no activity in the parts of the brain responsible for thought, sensation, emotion, or voluntary movement. She was in a persistent vegetative state.
However, her brainstem, specifically that lower hindbrain area, the medulla and the pons, survived. Because her brainstem was intact, her body continued to breathe on its own. She could maintain a heartbeat.
Right. Her eyes would occasionally open and move randomly, and she would occasionally groan, but she could not swallow, so she required a feeding tube for nutrition.
And this physiological divide between a dead cortex and a living brainstem sparked a bitter 15-year legal battle. Her husband argued that Terry would not have wanted to be kept alive with no conscious awareness and requested the feeding tube be removed.
While her parents, seeing her open eyes and hearing her groan, interpreted those autonomic brainstem reflexes as signs of communication and fought to keep her alive.
The courts ultimately ruled in favor of her husband in 2005.
The textbook notes that these cases continue to challenge us. It references a 2013 case of a 13-year-old girl declared brain dead after a tonsillectomy, and a 2013-2014 case involving a pregnant EMT where state laws regarding fetal life complicated her husband's directives. It is an excruciating boundary where neuroscience meets the law.
It truly is. Now, historically, from Phineas Gage to HM to Terry Schiavo, we only figured out what a brain area did when it was tragically destroyed. But today, we don't have to wait for an injury. We have brain imaging. My question is, how do you see inside a sealed bone box without opening it? Do doctors just have different types of cameras depending on the problem?
Basically, yes. It's all about how you interact with the tissue. To see inside, you have to bounce something off the brain or track something moving through it. The first approach uses radiation. A CT scan takes X-rays that pass through the skull.
Right.
Tissues of different densities absorb X-rays differently, allowing a computer to build a structural map. It's great for spotting a solid tumor.
But a CT scan just shows structure. What if you want to see the brain actually thinking? That brings us to PET scans.
Right. Positron emission tomography. In a PET scan, you aren't just taking a picture, you inject a mildly radioactive tracer into the bloodstream. When a part of the brain becomes active, it needs fuel. So blood rushes to that active area, bringing the tracer with it.
Oh, that makes sense.
Yeah, the machine tracks where the tracer goes, showing which parts of the brain are working during a specific task. But because it lacks sharp structural detail and uses radiation, the text notes PET scans are mostly replaced by fMRI today, though they are still used in specific research, like studying neurotransmitters in schizophrenia.
The second approach avoids radiation entirely and uses magnetic fields, MRI and fMRI.
An MRI places the patient in a massive magnetic field. This field actually forces the hydrogen atoms in your body's water molecules to align. When the machine turns off the magnetic pulse, those atoms snap back to their normal positions, emitting electromagnetic signals. Because different tissues hold different amounts of water, the computer can build an incredibly detailed structural map of the brain.
And the fMRI, the functional MRI, takes that same magnetic principle, but tracks the movement of blood flow and oxygen levels over time. It gives you highly detailed structure and real-time function.
Finally, we have techniques that don't look at structure or blood flow at all, but track the raw electrical output of the brain. The EEG, or electroencephalography, you place an array of electrodes directly on the scalp.
It measures the brain waves, right?
Yeah.
Like the frequency and amplitude of the electrical chatter happening beneath the skull. And because electricity moves so fast, an EEG is accurate down to the millisecond.
Exactly. The text highlights that this makes it the absolute gold standard for studying sleep patterns and sleep disorders. It's a perfect tool for when the timing of brain activity is more important than the exact geographic location.
I have to say, taking on the role of the student today has been fantastic. Thank you for guiding us through this. And to you, the listener, think about this. Every single word you just heard over the last several minutes was caught by your ears, routed up the spinal cord to your thalamus, bounced to the auditory cortex in your temporal lobe for processing, and hopefully is being bundled into long-term explicit memory by your hippocampus.
It is a remarkable silent symphony happening inside your head right now.
But I want to leave you with one final provocative thought. We spent a lot of time talking about neuroplasticity, the fact that the brain physically alters its structure, forging new synapses and pruning old ones, based entirely on new experiences and new learning. If that is true, what physical changes have occurred inside your skull just in the time it took to listen to this deep dive? Are you walking away right now with a physically different brain than the one you started with? Explore that thought.